Hi, this is Dr. Xu, teaching design of experiments for engineering research. In this video, we will talk about a slightly more complicated experimental design method. That is the Randomized Complete Block Design, RCBD. Let's look at this example. A hardness testing machine presses a rod with a pointed tip into a metal specimen with a known force. The hardness of the specimen is determined by measuring the depth of the depression caused by the tip. Now we wish to determine whether or not 4 different tips produce different readings on the hardness testing machine. We have determined to obtain 4 observations for each tip, so there will be a total of 16 runs. We formed the hypothesis testing as this. The null hypothesis is all the mean strength tested for all the tips are the same. The alternative hypothesis is that at least one pair of the tips produce different mean strength readings. There is only one factor, the types of the 4 tips. And we can design a completely randomized single-factor design using 16 different metal test pieces. However, there is a potentially serious problem with this completely randomized experiment in this design situation. If the metal pieces differ slightly in their hardness, this will contribute to the variability observed in the hardness data. As a result, the experimental error will reflect both random error and variability between the tested metal pieces. If the metal pieces differ slightly in their hardness, this will contribute to the variability observed in the hardness data. As a result, the experimental error will reflect both random errors and variability between the tested metal pieces. We would like to make the experimental errors as small as possible. That is, we would like to remove the variability between the different tested metal pieces from the experimental error. We select 4 pieces of metal material to be tested and cut them into 4 pieces. We will test each tip once on each of one of the 4 pieces from a metal material. Now we have 4 blocks. The 4 blocks are essentially different types of material to be tested. Of course, we will randomize which piece of metal within a block to be assigned to which tip, and also randomize the test sequence within each block. This is called a randomized complete block design. The word complete indicates that each block contains all the treatments. So tip 1, 2, 3, 4 in block 1, tip 1, 2, 3, 4 in block 2, and for block 3 and 4 as well. So each block contains all the levels of the factor. In this example, it is the different types of tips. Within a block, the order in which the 4 tips are tested is randomly determined. This design strategy improves the accuracy of the comparisons among tips by eliminating the variability among the blocks. The randomized complete block design is a generalization of the paired comparison design using the t-test. You can go back and review that video I posted previously and see the similarity of these 2 concepts. The RCBD is one of the most widely used experimental designs. The randomized complete block design is a way of reducing the impact of a nuisance factor. But we are not interested in that effect. If the nuisance factor is unknown and uncontrolled, such as random errors, we use randomization to minimize its impact. If the nuisance factor is known but uncontrollable, for example, atmosphere pressure and temperature during the process of conducting the experiments, now we will use analysis of covariance to compensate such nuisance factor. We will talk about this analysis of covariance technique in another video. If the nuisance factor is known and controllable, for example, in the example we just looked at, it is the different tested material. Other examples include different batches of raw material, different people, and different time, like different days. They are all common nuisance sources of variability. We will use blocking to systematically control and eliminate its effects. If we put the design arrangement in a table, it looks like this. We have 4 blocks, block 1, 2, 3, and 4, with different metal material to be tested, and the treatments are the 4 tips. All of them are randomly applied within each block. The generalization form of the randomized complete block design looks like this. We have B number of blocks and A number of treatments are randomly assigned within each block. We can generate this ANOVA table, calculate the F value, and use the P value to test the hypothesis. Now we have 3 sources of variation: the between treatment variation, the between blocks variation, and the variation from random errors. The total variation equals to the sum of these 3 variations, and the method of calculating the total variation is the same as we have shown before for the one-way ANOVA analysis. In the ANOVA table, the sum of squares between treatments is calculated using this equation. You sum up this term for each of the A treatments. B is the number of blocks. Y bar I is the average in the ith treatment, and Y bar is the total average for all observations. The degree of freedom is A minus 1. The sum of squares between blocks is calculated using this equation. You sum up this term for each of the B blocks. A is the number of treatments. Y bar J is the average in the jth block, and Y bar is the total average for all observations, and the degree of freedom is B minus 1. The sum of squares error is calculated using this equation. For each observation, you subtract the corresponding block average and treatment average, and add the total average. Square the result and add them all up. The degree of freedom is A minus 1 by B minus 1. That is the number of treatments minus 1 by the number of blocks minus 1. Now I'll show you how to perform the ANOVA analysis for the completely randomized block design in R. Using the example we have discussed before, assume we have recorded the result in Excel. The first column is the test sequence. It has been randomized within each block. The second column is the run number. This is how I label the sample so I know what to do with that sample. B1T3 means the material is block 1 type of material and I tested use tip 3. And the strength result is recorded in the last column. Make sure you have installed the Read Excel package so you can read the data from Excel to R. In R, I set my current working directory to the path where I stored that Excel file. I load the Read Excel library, read sheet 1 from the Excel file using this function and pass the data as a data frame to strength. I'll copy the code to R and enter. As you can see, the data is stored here. If I double click the name of this variable here, you can see the table from Excel has been copied to this data frame. We will use this str function to see the format in each column in the data frame. Type in the code and enter. We can see that the run number has character values, so they are all characters. And other columns has numeric values. See here, and the 3 numeric values here. We need to specify the tip column here is a factor. Also, the block column is a factor, although the block factor is a nuisance factor that we are not examining its effect. We use the asFactor function to change a column to a factor type. In this line of code, I change the tip column in the strength data frame as a factor type and pass the value back to the tip column in the strength data frame. I do the same thing for the block column. Execute these 2 lines of code in R here. Now, if I check the structure of the strength data frame, you can see that the tip and block column is changed to factor with 4 levels. I use these 2 lines of code to perform the Anova analysis and display the result. So in here, I want to see the tip and blocks impact to the strength column in the strength data frame and store the data here. I copy the code to the RStudio and enter. As you can see, the result is shown here. This is the p-value for the impact of the tips. For the hypothesis testing, the p-value for the tip factor is smaller than 0.05. So we reject the hypothesis and conclude that different types of tips do impact the strength test reading. Although in this example, we don't care about whether the block, that is, different type of testing material, impact the test strength readings, we can see here that the p-value is 0.48. It is larger than 0.05. That means it does not have impact on the test strength readings. In this example, if we design and analyze the data using the completely randomized single-factor design and one-way ANOVA, we probably will reach the same conclusion that 4 types of tips do impact the strength test readings. But if we don't know this ahead of time, we cannot separate the impact from the tips and the test material. Thus, this completely randomized block design is more accurate. And this is the correct way of doing the experiments. Going back to the initial question we have here, we now can conclude that the 4 different tips do produce different readings on the hardness testing machine. I have summarized the R script used in this video here, and it is also posted in the first comment down below this video. To conclude this video, we have introduced the design and Anova analysis for the randomized complete block design. In the next video, I will show you how to present the data and perform data adequacy checking. Please leave a comment if you have any questions. Thank you very much for watching. If you feel this video is helpful, please subscribe, like, and share. This is Dr. Xu. I will see you in the next video.